Well, welcome everybody to the 2021 Global Institute for Water Security Distinguished Lecture Series. My name is Jeff McDonald. I'm the Associate Director of the Global Institute for Water Security, and it's my extreme pleasure to welcome our speaker, who I'll introduce shortly, and to kick off this year's seminar series. We have 84 registrants, and of course, this serves multiple purposes. It's a so-called 990 program for many of our Masters of Water Security students, both in Saskatoon and those at Beijing Normal University. Some of those students will be watching a recorded version of this, so I want to welcome all of you. This is also underwritten by the Global Institute, but also our Global Water Futures program led by John Pomeroy, and I want to thank Global Water Futures for their support and welcome the broad family of researchers who are part of the Global Water Futures program. And thank Jay Famiglietti, our director, for sponsorship of this event as well. We are going to have about 7 or 8 lectures, I guess, through the fall. They will all be on Wednesdays at 10 a.m. local time in Saskatoon. The lectures will run for 1 hour. And then each day or each week, there will be an opportunity for early career researchers to stay on the call and have a conversation with the speakers. And I will moderate that, and this will be wide-ranging on topics of science, early career issues, or anything else you'd like to engage our speakers with. They've agreed to be fairly flexible in their openness to discussions. And I think that will be a really rich experience, particularly for our early career researchers. But today, without further ado, I'd like to welcome Professor Hannah Cloke. Hannah is Professor of Hydrology at the University of Reading in the UK, and she's co-director of the Water at Reading program. And Hannah is known internationally for her leadership in the area of flood forecasting and risk management generally, although she has many topics within that broad rubric. And for that, she's been recognized by many groups and professional societies. She's received the Phineas Medal from the European Geophysical Union, the NERC Early Career Award, the British Hydrological Society's President's Prize, and I guess as someone who holds a British passport, this is really quite incredible for me. She's also Officer of the Most Excellent Order of the British Empire, OBE. So in fact, probably I should be referring to her as Dame Cloke. But anyway, I've known Hannah since her PhD days, and it's just so great to witness her career development and how extraordinary she's done in these last 20 years or so since getting her PhD, and to welcome her today. And Hannah, I'm only sorry we can't see you in person in Saskatoon, but that'll have to wait to another post-COVID visit. But Hannah, I'll turn it over to you for sharing screen. And again, thanks so much for being with us.
Thanks so much, Jeff, for that lovely welcome. It is really fabulous to be here. You know, I am sad I'm not in Canada, but you know, this is a good second choice. So some acknowledgements. I just really want to say that I work with huge teams of people, so all of the things I'm going to be talking about today have come from those teams. Okay. So who am I? I've had a little bit of an introduction from Jeff there. I co-direct Water at Reading with Liz Stevens here in the top picture. And we have a diverse team of researchers who have been depicted at the top here in our virtual portrait this year, because of course we're spread all over the world actually and have only been able to meet up virtually. And this portrait was done by Kelly Stanford, who's a brilliant portrait artist and scientist as well. And she also did this portrait of me down the bottom here, which you can see with my hair in these crazy stripes. And I don't know if any of you have seen this before. These are the climate stripes developed by my colleague at Reading, Ed Hawkins. He's a professor of climate science, and it shows the change in the global average temperature over the last 100 or so years by showing kind of blue for the colder colors and red for the warmer colors. And so if you start on the right-hand side of these stripes, okay, that's today. And then you kind of go over to the left, and that's kind of 100 years into the past. And you can see by this visualization quite how strong that climate warming signal is. I find these kinds of visualizations really helpful because it's just such a simple way of looking up what's going on our planet. And you can go and have a look yourself wherever you are in the world. You can go to the website and download your climate stripes and use it to start conversations about climate change. I spend most of my time in Reading, which is a town just to the west of London in the UK. And I also have a guest professorship at Uppsala University. And I'm also a fellow at the European Centre for Medium Range Weather Forecasts. So I get pulled in lots of directions, but I have lots of fun. So I study, well, I am probably quite obsessed with floods and rivers and also other natural hazards. So I'm going to take you on a tour of some of the most dangerous and destructive natural hazards that the world faces. And I want to show you what lies beneath these murky floodwaters and how science is helping people to live with these floods in the future. But first of all, have a little think. What does flooding mean to you? What's conjured up in your mind when you think of the word floods? And perhaps it's some of these images you might see on the news, you know, entire housing estates covered in water, or the sun glinting off the flooded fields, or people being rescued here from their houses by volunteers, or perhaps in boats or helicopters, or bridges collapsing, you know, subways flooded, cars being picked up and floated away. Or perhaps you have been flooded yourself. And so you really understand how it feels to have your home invaded by this thick, mucky, dangerous water. So I've got colleagues here at the university in Reading working with flood-hit communities in the UK, particularly the most excellent Fiala Mehring, a researcher at Reading. And she's highlighted the extreme psychological trauma that is caused when your home is flooded. And it's like similar to like being a victim of crime, really, or suffering a bereavement. And some people take years to get over it, you know, even after the houses have dried out. They suffer from post-traumatic stress every time it rains. So if you're at home right now, or perhaps you're in your office or wherever you are, just have a look around you and think about what it would be like if everything there is destroyed. Now, use your imaginations here, okay? Think of your family photo albums. Think of all of the priceless memories that you have got lying around, kind of trashed. And for me, I always think about this music box. I don't know if you can see that. My grandmother gave this to me. It's no longer with us, but it's very, very precious to me. And it's full of precious stuff that you can judge me what you will. But it's got, you know, really, really lovely things. And if the floodwaters picked that up and you know, it floated away, you know, down the hallway, I'd be, you know, absolutely traumatized. So try and think of something really personal all the way through this talk, because it really brings those floodwaters home, and really employ your imagination. So we're going to go around the world a little bit and look at a couple of floods, as long as I don't talk too long about one thing, and look at some of these really destructive floods. So I'm interested in forecasting, and I do that using Earth system models. And that basically means a huge computer model of the Earth and where all the air and the water and the energy are going all the way around the globe, and tracking that. And it's the same types of models that we use in weather forecasting. So you're all familiar with weather forecasts telling you whether it's going to rain tomorrow or next week. We use the same types of models, and it's just kind of got floods on the bottom of it. And it's got all the processes from like the ocean and the atmosphere and the land surface as well, moving kind of mass and energy around the globe all the time. And so this is the Earth system approach. And we use that for floods, but we also use it for forest fire forecasting, heat wave forecasting. So lots of natural hazards, thinking about, you know, what can we say, what's going to happen in the next hours, what's going to happen in the next days, what's going to happen in the next weeks. And looking weeks ahead, that's what I mean by forecasting in this sense. So why would we bother to do this? Well, one reason is that it makes financial sense. We did some experiments with the European Flood Awareness System, a European scale flood forecasting system, and worked out that the benefits are on the order of 400 euros for every €1 that you invest in this early warning system. So, that makes sense for governments to do that, right? And it makes sense for insurance companies to be interested in this too. But of course, something much more important is that it can save lives and it can save livelihoods. So we work very closely with teams at the Red Cross Climate Centre and other humanitarian partners. So you can take actions before a flood happens. You can get people out of the way. You can provide water, fresh water drinking cans, and you can divert water and evacuate people. So these are the things that motivate me the most. You really can make a difference by saying a day in advance, a week in advance, that a bad flood might be coming, using these very large system models. So I'm a flood forecaster, but I have to consider the science at every single scale, from the physics of the very, very tiny, where all the individual molecules are going and how they interact with each other in the world around them, to the physics of the massive, so big oceans, drawing up water, evaporating down into some of the biggest rivers on Earth. And using the Earth system approach, we need the fastest supercomputers in the world to do all of these billions of calculations to predict how all of these things interact. And even so, it's really hard. It's really, really difficult to predict floods. But we are actually now managing to do this on a global scale. And certainly when I was a PhD student working with Jeff, that was not possible. So this is really quite a recent thing that we can do these global scale flood forecasts. Before the rain's even begun to fall, we can say with some certainty when and where it's going to flood. So lots of different people are using this information to take early action, to save lives, protect communities. And that's really what motivates all this work. But how big a problem are floods? I mean, I'm sure all of you have been watching the news and seen that it's been quite bad this summer in terms of floods all around the world. Is the problem really getting worse? This is a question that gets asked all the time. The short answer is yes, it's a really, really big problem, however you measure it. And yes, they are getting worse. And this is for a number of reasons. According to the UN Office for Disaster Risk Reduction, floods were accounted for 44% of all disaster events between 2000 and 2019. And they affected 1.6 billion people worldwide. And they are deadly. So the June 2013 floods in India led to more than 6,000 deaths. And that's just, one flood event. And we've seen, obviously, some terrible floods killing people this summer too. And in many places, floods have been getting worse because of where we choose to live, or more often, where we have no other choice but to live. It puts people into the way of the floodwaters. And we also put more people at risk because of the way that we've changed the landscape. So we've built whole cities on floodplains or at the coast. We've cut down trees that help to hold the soil in place. And because humans have changed the climate, we've got more heat and more energy in the oceans and the atmosphere. And that makes the extremes of weather more extreme than we're used to. Climate change is causing more extreme weather patterns, heavier, more intense rainfall, longer rain events that last, days or weeks. So when a system gets stuck in one area, or a series of rainstorms that comes one after the other, kind of clustering close together. And in the past, like scientists, hydrologists, climate scientists were really hesitant to say, oh, climate change causes a particular flood, because it is really complicated. And rivers and lands, they've flooded, since before humans existed. But you can say now with increasing certainty that, you can see these human fingerprints in the floods that we've been seeing. And that, that's terribly frightening. And what's very clear is that we definitely need to be much better prepared for the floods that are happening. They are more intense, they're more frequent. And we know that floods are hitting people in displaced and poorer communities much harder than they're hitting those in the developed world as well. So here's a little picture of some mountains, okay? And each mountain represents a little bit of a step in the forecasting to what actually happens on the ground. So, you know, I do a lot of flood forecasting using big fancy models. They're really, you know, loads of supercomputers. We need to feed them with observations from satellites and on the ground measurements as well. And then we can do the weather forecast to say where it's going to rain. And then we have to get all the flooding going on so we know when and where the flood is going to be on the rivers or perhaps at the coast. And then you need to know what the impact of those floods are as well. So you need to do some socioeconomic modeling to understand the impact. But then you have to be able to issue a warning in a timely way. You need to know what the consequences of that warning are going to be. Someone needs to take that decision. And that's really such a key part of the chain and often where things go wrong. And then the last mountain here is the decision. And that is where people are getting out of the way. They are listening to the sirens going off. You know, they are choosing to take that evacuation seriously or protect their house in some way. And all of these bridges can fall down at any point. So it is a really complicated system. I work mostly in hazard forecasting, but you have to understand that everything is linked along all of these bridges and make sure all of those bridges are standing, because otherwise there's no point in doing all of this fancy modeling at all. So I'll come back to that at the end, hopefully. But for now, let's go traveling around the world, because we can't do that at the moment. So we're going to do it virtually. And we are going to go to Mozambique, which is down here in Africa. And we're going to meet some people. Mozambique's a pretty big country. It's just north of South Africa, and it's got a population of around 30 million people. And most of those people live in extreme poverty. In technical terms, UNICEF said that more than half of the population lives on less than 50 cents a day. And that number includes more children than adults. The Human Development Index evaluates life expectancy and access to education and gross national income. And Mozambique ranks 181 out of 189 countries on this index. 70% of the total population lives in poverty. A huge number of children are suffering from chronic malnutrition, and very few have access to safe sanitation, including the risks of disease. Most of the population live along the coast and these fertile river valleys. So that means that when a flood does come and does happen, that much of the population is in the way of the waters. And Mozambique is no stranger to floods. So large floods occur on average every 2 to 3 years, really quite big floods. And according to the Global Facility for Disaster Reduction and Recovery, Mozambique is Africa's third most dangerous country in terms of its exposure to weather-related hazards. The coast of Mozambique is regularly battered by these tropical cyclones. So what do I mean by tropical cyclones? You've probably known them as hurricanes, but they are tropical cyclones when they hit Africa. They're the same thing as hurricanes, so they're the most powerful storms in the world. This must be a familiar image to some of you. They're hundreds of kilometers across, and they cause strong winds and storm surge from the sea and heavy rains that lead to flooding. And the warm waters of the Indian Ocean here fuel the storms as the water droplets are continuously evaporating and building up into the clouds and forming the structure of the storm. So back in 2000, there were huge floods caused by Cyclone Idi, followed just a few days later by Cyclone Gloria, and rivers such as the Limpopo, the Maputo, and the Buzi and the Save saw record levels of flooding, which devastated large parts of southern and central Mozambique. And more than 5 million people, so that's 5 million people, were displaced and affected by the flooding. We've already said that a lot of those people are very poor indeed. The Limpopo River, which is already one of Africa's biggest rivers, swelled, and it reached like 20 kilometers across in some sections. I don't know how many of you are familiar with Tower Bridge over the River Thames in London. It's the one with the kind of the two big towers on it like this. It's all in all the James Bond movies and things like that. So if you imagine 100 tower bridges in a row, that's how wide the river became at that point. And normally it's, you know, a relatively small river. So there was another big flood in then 2013. And there were days of torrential rain throughout January, and the main rivers in the southern areas and central areas of Mozambique flooded as well. There was more than 200 millimeters of rainfall in a day. That's 8 inches, I think, in less than 24 hours. I'm really bad at my millimeters to inches conversion, forgive me. But the town of Cloke, which we can see down here on the map with the red bits showing the flooded areas, is on the bend of the Limpopo River here. And there's a really lovely restaurant there actually that serves excellent chips. If you're ever in Cloke, go and get some chips. Anyway, it was completely flooded, the town, and you can still see the flood marks on the wall there. It killed 40 people just in that town, and there were 150 people evacuated to temporary accommodation. So Mozambique is no stranger to floods. In March 2019, Cyclone Idi hit Mozambique twice. So this was unusual in itself because of the way that the storm kind of tracked from the ocean over the land before going back out to sea and then coming back in as this monster storm. So on its first visit over land, it was quite a weak storm, but it brought enough rainfall to cause flooding in Mozambique and Malawi. And then the second time it came in, it was a strong tropical cyclone, and it had winds and rain and floods that caused huge damage and affected more than 3 million people. And then while the country was just starting to clean up, just 6 weeks later, another tropical cyclone, Cyclone Kenneth, slammed into northern Mozambique. And this was the strongest cyclone to hit Mozambique in modern history. So we're going to take our tour now right into the heart of this monster. You know, what is being in a tropical cyclone really like? And usually the first thing that comes to mind when we hear about hurricanes or tropical cyclones is the destructive winds. So you tend to think about the dramatic pictures you see on the news with swirling clouds like this, but also palm trees bending over in the wind like this, and debris from buildings being thrown around. And so the noise and the sight of the wind is pretty dramatic, yeah. But in many cases, the water can be much more dangerous, both for people and for property. Coastal areas can be extremely vulnerable to waves whipped up by the wind and storm surges, which is when you've got like a low pressure in the center of the storm, and it lifts the sea levels up several meters above what they would normally be. And then you've got winds blowing that water onto the coast as well. So you get a massive rise in the sea level in the storm. If you're further inland, with many people living beside these rivers in these fertile river valleys, people are really vulnerable to the heavy rainfall. And there are flash floods and landslides, and then downstream, the rivers expand out over their floodplains. So the impact of the rainfall and the floods are the longest lasting. So long after the storm has blown away and the wind has died down, the floods are still there. And what makes it especially bad is that severe flooding cuts off communities from the outside world, which prevents people from getting into the worst areas with the help that they're trying to bring. And often humanitarian aid agencies are desperately trying to help during the weeks and the months after a cyclone, but they just can't access the people in the areas that need it because the roads are underwater or destroyed and bridges have been washed away, and you need a helicopter to get anywhere, and there are not many people with helicopters in Mozambique. So it's therefore essential for humanitarian and civil protection agencies to have the right information on upcoming rainfall and flood risks, so they can get people out of harm's way before the storm hits, and then even deliver the aid to places that will need it in a few weeks' time. So this here, a complicated map, but it's quite pretty, hopefully. It's the European Commission's Emergency Response Coordination Centre's daily map for tropical cyclone Idi. And you can see the huge rainfall accumulation. So that's the really, really very blue bits. And here we can trace Idi as it kind of is a tropical depression, and it swings around and intensifies over the Mozambique Channel, and then it loops back and slams into Beira, which is a port city of 500,000 people. And we can also see down on the bottom of the graph there, a 4.5 meter storm surge. Possibly it got up to 6 meters high in places, which is about 20 feet tall, or as tall as a giraffe. Okay. And here on the right of the image, you can see the red area flooded, which has been located by satellite mapping. As a tropical cyclone makes landfall, the surface friction increases at the front edge of the storm as it moves over the relatively flat sea to the lumpy, rough land. And this in turn pushes more of the air, up into the eye wall, which is the central column at the heart of the storm. And that increases the vertical motion of the air occurring there. And this convergence sucks up huge amounts of moisture-laden air, which then falls out as rain. And this is what's responsible for these torrential rains associated with tropical cyclones. After landfall, Cyclone Idi quickly weakened, but it continued to move slowly inland, resulting in continuous rainfall for several days that led to widespread and devastating flooding in central Mozambique, especially in the Pongwe and Buzi rivers, which flow through Beira. As is often the case for such floods, we have no idea how bad the floods got because no one was able to take measurements in such conditions. And any of the automatic machines which are designed to measure the river levels were completely overwhelmed or destroyed. But we do know that rivers went up extremely high and extremely fast in the days following the landfall. And then this water stayed there for a really long time, taking weeks to go back down again. So this is just one of the difficulties of doing science in a disaster zone. And even worse for the flood experts in the area, the meteorological office in Beira was completely destroyed by the storm and the floods, along with decades of precious data, which had been painstakingly assembled by hand and then stored in these handwritten notes for decades. And all of those valuable local climate records are now lost forever. So the seasonal wetlands turned into these inland oceans full of muddy floodwater. And in Sofala province, where Beira is located, the floods were more than 50 kilometers across this time, which is about 30 miles wide. Satellite estimates suggest an area approximately 16 times the size of England covered in water. Now, I'm not sure how that relates to Canada because I'm not very good at my geography, but it was pretty big, basically. So less than 6 weeks later then, just as this recovery was beginning, another tropical disturbance began to organize to the northeast of Madagascar and move westwards towards Mozambique. And that was this tropical cyclone Kenneth. It rapidly intensified. It was declared a tropical cyclone on the 24th of April, and it had 10 minutes sustained wind speeds of 215 kilometers an hour. It weakened a little bit, but then slammed into northern Mozambique near Pemba. Now, in the period from 1950 onwards, just 12 tropical cyclones have reached this intense tropical status in the Southwest Indian Ocean during the month of April, and Kenneth was the strongest of these. And the result was severe flooding again, particularly across the Cabo Delgado province of northern Mozambique during the days following Cyclone Kenneth's landfall. There was an estimated 45 deaths and the destruction of at least 2,500 homes. Also, the loss of a significant number of crops and fishing boats and equipment, which of course is really important for people's livelihoods. So let's meet some of the people at the center of this. Here on the right is Jano. The Mozambique Red Cross was already working on development projects in the area before the cyclone hit. And because they were there, the volunteers from the Red Cross were able to warn people right in the communities to take cover, move to higher ground. And when the cyclone did hit, they were able to evacuate people and provide immediate help to the communities. So Jano Dambo here works for the Mozambique Red Cross and is one of our research partners in Mozambique. He was kind enough to provide me with this whole series of photos, so thanks to him for them, of the flooded communities, of the aftermath of the cyclone, and tell his story about what actually happened. So you can see Jano here in Beira in the floodwaters caused by Cyclone Idi. And here you can see Jano and some Red Cross volunteers unloading the consignment of blankets, mosquito nets, tarpaulins outside of the Red Cross office for Sofala province. On the wall behind there, you can see this logo of the Mozambique Red Cross. Much of the time, the Red Cross's work in Mozambique is spent with rural communities, helping with health programs such as immunizations. But in the country where you've got this really hazardous weather combined with such poverty, they spend a lot of time just kind of responding to the human disasters that follow storms like these. And you can see that Jano here is wearing a German Red Cross t-shirt, and this is because the German Red Cross support the Mozambique Red Cross in setting up this idea of forecast-based financing. So this idea means that instead of waiting for a disaster and then going and asking donors for money to help in rescue and recovery, you can release that money before something bad happens by using the forecasts of tropical cyclones and floods and other hazards, and then look at the forecast to see if something bad going to happen, and then release that money so that the preparations can be made. The Mozambique Red Cross work with the International Federation of the Red Cross, who help to provide equipment and resources to help with this work. Now, I often work with the Red Cross, and my Reading colleague, Liz Stevens, is seconded to them because they're actively seeking to draw in this science to what they do and use it through their international network in developing countries. So they've got these really strong networks that can respond to natural hazards when they do occur. The Red Cross were in no doubt about the seriousness of this crisis, and they said, you know, this is the worst humanitarian crisis in Mozambique's recent history. It's a humanitarian catastrophe for the people of central Mozambique. Large parts of Beira have been damaged. Entire villages and towns have been completely flooded. Rescuers are scrambling to pull people trapped on rooftops and in trees to safety. Many, many families have lost everything. And the scale of the destruction was huge. Around 1,000 people in total are thought to have died, and 2.5 million people required humanitarian support. So flooding is truly monstrous. But let's bring our tour further away from Mozambique and Canada and land you right back in Reading in the UK. We're going to move from tropical cyclone Kenneth to the River Kennet. This is my local river, okay? I'm sure many of you, like me, have found this kind of year and a half or whatever we've been doing of online life rather tricky. So my favorite antidote to the hours and hours of back-to-back online meetings that my life has become is to take a walk or a run over to this river and follow the swirling song of the River Kennet as it flows into the River Thames here. So this is the Thames in the background. The Thames is flowing from the left of the picture to the right towards London, and the Kennet is flowing from the foreground right into the River Thames here. And I really literally stand on this spot, mesmerized by the water. People are always looking at me strangely. My family looks at me strangely, but I love it because I love the way you can see where the waters of the two rivers meet. And then they run along side by side for a while. And the way the water kind of tumbles over itself in ropes. And you can see the eddies spinning and circling. And you can see the dance of the sunlight and the wind-blown patterns on the surface. You can see upwellings of water that look like hippos rising. But they're always completely unique. And it's like a display of nature just for me, never to be repeated again. Now we're going to zoom over to South America and see beauty in a river on a much larger scale. This is the River Amazon, and this is the image I have permanently on the backdrop of my computer. So I can actually see 4 of these at the moment because I've got so many screens. I stare at this all day, sometimes even when I'm pretending to look at my students or colleagues in an online meeting, but obviously don't tell them that. But look at the way that the river loops and meanders and threads. It's pushed into these extraordinary shapes by the conflicting forces of physics and chemistry and biology. And I find this image a bit like a puzzle because the closer you look, the more tributaries you can see, these tiny meandering baby rivers. And this is a huge river. So rivers are beautiful in both their simplicity and their complexity, and the swirling and the threading and the beautiful chaos of the river flow. And it's this complexity that really intrigues me and inspires me every day. But also it's essential to be able to work out how rivers flow and predict when a flood is coming. Because as we've seen from Mozambique, rivers are beautiful, but they are these beautiful monsters. They have these split personalities. They draw people in to live beside them when they're peaceful and provide food and transport. But then they quickly change character and they destroy everything around them. So what we really want is the power to be able to benefit from rivers when they're good, but to know in advance before they go bad, with enough advance warning to take action to protect the people and the communities. And that's the aim of flood prediction. But it's a really hard job. So why are floods so difficult to predict? Well, weather predictions have come a long way in recent years. So today's 3-day forecast is as accurate as a 1-day forecast was in the 1990s. But as we all know, they're never perfect. Rainfall and snowfall, hardest parts of the weather forecast to get right. And these days forecasters are pretty good at getting the temperature or the wind speed, but on many occasions we still struggle to predict exactly how hard the rain is going to be and exactly where it's going to fall. And that's because we have to be able to predict a lot of different complicated underlying conditions to make it rain. The temperature of the air, the humidity, the direction of the wind, where the clouds are, what type they are, how big the clouds are, and even then forecasters can still get it wrong. If you multiply all the uncertainty within the weather forecast with the complexity of modeling exactly where the water is going to go as it hits the ground, when it hits the ground, how it travels through the landscape, both on the surface and under the ground, then you start to get an idea of the difficulties that we as forecasters face. So in effect, we have to take account of all the possible different routes through the landscape that a single raindrop might take. There are billions and billions of different possibilities. So if we want to stand a chance of knowing what will happen in the future, this requires a lot of assumptions about what will happen now. So standing here at the Kenneth mouth, when I'm watching the water flow, I think about all the many, many droplets that are passing by me right now. So where did each one of them come from? Which pathway through the landscape did it take? When did each drop fall as rain? And it can seem like an impossible task to try and understand the flow of a river. So sometimes I like to imagine that I have superpowers and that I can see every single droplet. And I imagine I can see each droplet clearly as individual blue pebbles. So I've got these props here. These are my little blue pebbles that I imagine. So each of these drops of water has its own history and its own destiny. And if you imagine that you can see them all and read them all and follow them all, then we can take this journey through time. We can kind of stop time. So slow it down and stop that river and zoom in and then see all of the individual droplets of water. And each one's like a different size. It's made up of a different number of molecules and it's got its own history. And then we're going to follow each droplet back to its source and rewind time a bit. So maybe this one fell in some really heavy rain yesterday in a street in Oxford, which is quite close to Reading, and has rushed over the land straight into the river. Maybe this one fell in some rain at the weekend in the hills, right at the headwaters of the river. And it's been working its way down through the tiny brooks, the streams, and then the bigger and bigger rivers. And perhaps this one fell, last March, while we're in a lockdown, and it's been sitting in the soil, waiting to get pushed out in the latest rainstorm. And perhaps this one fell in the summer of 1978 when I was born and has percolated down to the groundwater where it slowly made its way through the rock until it was finally discharged into the river. So I always try to imagine which drops I see, were from the day when I was born. I think this idea of droplets is captured really brilliantly by this wonderful poem by the fabulous Kathleen Raine. It's called Light Over Water Brilliant. Myriad instantaneous alighting raindrops on a stream that has run unbroken down and on since this once familiar place was home. Each in its alighting flashes sun's glitter and is gone as another and another and another come to meet me, Angel after angel after angel, its dancing point, always here and now, the same bright, innumerable company arriving, anew the present, always absolving from time's flow. Old, I know, how many, many, many the epiphanies of light. Anyway, a little bit of poetry for you. But the next time you look at a river, take a moment to stop and go beyond that mass of swirling before you and zoom in and look for those blue pebbles and ask yourself, where did they all come from and when did they all come from? All of this is part of this Earth system cycle. And these blue pebbles of water have been around this cycle several times, you know, evaporated up from the land and the sea, transported by the wind and rained down upon the land again and again. And it's trying to recreate this system in a computer model that allows us to forecast the floods. We can use the idea of an Earth, a giant natural system, to trace the billions and billions of pathways of water. And we aim to predict where they'll go across the land, through the soil to reach rivers, and ultimately downriver to where people live and work. I work with a large team here with the Copernicus Emergency Management Service for Floods, which provides open access global early detection of floods up to 30 days in advance. In March 2019, I was part of the team of forecasters using this Earth system way of flood forecasting, putting it to the test. And we analysed the tropical cyclone track forecasts. We looked at where and when the cyclone might make landfall, but also where it might be dumping all of the rain it was bringing with it. Several days ahead, tropical cyclone track forecasts indicated that both cyclones, Idi and Kenneth, were problematic. And the global flood awareness system indicated severe flood events. So we provided emergency reports to the UK government and to our humanitarian partners, such as the Red Cross, including the Mozambique Red Cross, to detail the upcoming flood risk. And we were able to provide them with this crucial information, which would previously have been impossible to know. Where would the cyclone move next? How much rain was expected? Which rivers were likely to flood and when? When would the floodwaters recede? What areas are likely to be inundated by the flooding and how many people were at risk of flooding? And the idea is that this early warning means that actions can be taken to prepare for these devastating impacts. So what did happen? Well, the Red Cross and the UK government told us that this was the first time that flood risk information had been provided in real time and that it was extremely valuable to help them plan their aid efforts. And we know that our reports were used alongside other information to help inform decision-making at a number of levels. So international, UN OCHA, through to the Mozambique Red Cross on the ground. And the key contributions seemed to be that it was assisting in creating this situation overview. Where and when was the flooding likely to occur? Where were most people at risk? Where are you going to send the boats that are going to rescue people trapped on rooftops? And the aid agencies used our reports to send assessment teams to the correct area and move aid items and equipment to the places where they would be needed the most. And Jano from the Mozambique Red Cross said they were able to give out chlorine so people can purify their water. And emergencies like this one, it's really common for the clean water sources to be contaminated with dirty floodwater. And with roads still cut off, the Red Cross used supplies already stored in Mozambique to help people. So that included shelter kits, tarpaulins, blankets, sleeping mats, buckets for clean water. And malaria is always a problem there. So they gave us, they gave out mosquito nets, and thousands of people were evacuated by boat. So this is all very encouraging, and perhaps we as hydrologists and forecasters did make a difference. However, forecasts and early warnings are not useful in a vacuum. So that brings us to my next stop on our world tour, which is the United Nations here in New York. New York seems to be not on the tour at the moment, sorry. Woo! Sorry. There we are, we're back in New York. So we have to ask ourselves, are we making the best use of science for humanitarian emergencies? By running a computer model in Reading, delivering forecasts to aid agencies in Switzerland, sending that out to workers in Mozambique. Is that the best way to support people of that country? Are we making them dependent on another source of overseas aid? It is very, very complicated. And my experience of working in Mozambique clearly showed me the depths of the murky waters of these competing national and international power and wealth issues. You know, we have the capability to help when floods happen. We have the technical capability. We have an even stronger duty to build up national capacity and capabilities for forecasting and early warning. And the destroyed meteorological office with its destroyed handwritten climate records really brought that home to me. Developing scientific capacity takes time and money and political will. And in the meantime, the cyclones just keep coming. And so, who should take responsibility for delivering all of this information on the forecast, the risk and the impact? And where do we as forecasters have a role? And these remain open questions. So I talked about the climate stripes at the beginning. I'm often asked how climate change is making floods worse. These are the climate stripes from Mozambique. And you can see very clearly that Mozambique has been shifting unmistakably towards the red. This is happening across the world. Now, it's really difficult to link the flooding between tropical cyclones and Mozambique and climate change. It is a complicated picture. It's not one that we understand fully. So just because rainfall is being affected doesn't mean that the floods will naturally follow as well, because of course it's where people are going to be in the way. But it is possible that we're getting a much higher frequency of these high intensity storms. We know climate change is causing heavier, more intense rainfall, and we know sea levels are rising. And the flooding was more intense than it would be without the climate change. So perhaps you're aware of the recent flooding in Europe in July. There was some terrible, terrible flooding. And this picture is really just, is quite shocking. This is a place that is not used to these types of very high death tolls and destruction. There's an assumption that Germany is a country that this doesn't happen to. I worked with the European Flood Awareness System, which is part of the Copernicus Emergency Management Service. So I'm an attached researcher to the system. And we were looking at this flooding days ahead on the system. And we could see it was coming. We could see that there was, warnings out across Europe for this very serious flooding, both of the rivers and for flash floods in the mountains. If you want to go and have a look at the Copernicus Emergency Management Service, you can follow this web link down the bottom. You can look at GLOFASS for free, and you can look at EFAS, the European one. You can look at past forecasts for free as well. So do go and have a play with that, should you be interested. So this is the forecast of that we got from the 12th of July. And it's just to highlight quite how much of Europe was flagging up as, there's a problem coming, something's going to happen. You can see this is what's called an Ensemble Hydrograph down the bottom. But all you need to notice is that the river level is rising right into this kind of purple, serious flood zone here. So it was very clear across Europe that there was a large event coming. But lots and lots of people died. Lots of people were reporting on the news. We did not know this was coming. We had no warning. We didn't expect this to happen at all. So clearly, if I could see this sitting in Reading on the forecast several days ahead, but the people on the ground did not know it was coming or chose not to listen to the warnings, then this whole system, this whole kind of mountain to mountain bridges is designed to save lives, needs people to act on warnings before the floods arrive, but it did not work as it should have done. And some of those bridges broke down. Exactly where is a good question. There's a lot of rhetoric about it just being because of climate change, but I like to think, just blaming it on climate change is no good. Saying that the system functioned perfectly, but it's all to do with climate change, that's not right. I like to think of it as, saying the maiden voyage of the Titanic was completely successful because it made 99% of its journey safely or something. It's no good. So something is going wrong in this chain, which is why you must consider everything all of these different bridges. And if you want to read a bit more about my opinions on this, which can be very strong, and I get a bit angry sometimes, you can have a look at this article in the conversation that I wrote about what might have gone wrong. And also, if you're interested, there's a little YouTube video of from the Royal Society Summer Science Exhibition, what happens when there's too much water, if you want to do some more trips of the imagination, because it is about imagination flood forecasting and helping people see the invisible. I asked you to use your imaginations at the beginning. I asked you to imagine seeing these blue pebbles. You know, what is the use of a perfect forecast if the people it's supposed to warn can't see the danger they're in? What's the point in using a giant computer model to predict what's going to happen if people don't know what to do in a flood? Effective flood warnings require people to be able to see the future and imagine their house full of water, to assess the likelihood of that happening and to see the multiple paths that they could take to keep them and their family and their property safe. Here we've seen in Germany, we've seen what happens when people can't visualize the threat of a river ripping down their street or a lake appearing in their house. And these elements of flood warnings must improve. And you have to have a really long memory to understand the risk of flooding, much longer than a human lifespan. There have been big floods in these areas before, so we really must engage our imaginations. I like to engage people's imaginations through a lot of different ways. Sometimes I dress up as a unicorn, which is always a sight to see, I'm sure. And I also like to try a bit of poetry. As you notice, I'm getting more and more into poetry. But the point is that you must try lots of different ways to capture people's imagination if we're going to make any difference in this area whatsoever. Now, I've gone way over time, probably. Sorry, Jeff.
You're good. You're good. Well, thank you very much, Hannah. That was really a fantastic talk and tour around the world. And we're going to open it up for questions. I'm going to try to activate the live transcript, and that might make it easier as people unmute to both see and hear the question. Enable auto transcript. Let's see how that goes. Sometimes this can crash the system, but fingers crossed that won't happen. You can also type into the chat. So we have about 7 or 8 minutes for questions. And then just as a advance warning for those early career researchers that would like to stay on for a conversation after the top of the hour with Hannah, then you're very welcome. Hannah, maybe I could kick off while we wait for people to unmute or raise their hands. I see Martin Clark has his hand up. I loved your idea about the blue balls and thinking about, you know, tracking raindrops almost. Yeah. And, you know, that's what many of us do studying runoff processes. But it almost seems that under these extreme events that, you know, it's overland flow, either infiltration excess or saturation excess. You've got such widespread flooding that maybe those details matter less, some might argue. I'm just wondering if you can reflect on the need for kind of runoff mechanisms in the face of something so extreme, where maybe those kind of nuances are, you know, not so useful. I say that knowing that some of these large European floods that have been sampled isotopically have shown that the bulk of the flood water is water that was stored in the catchment prior to the event. So that sometimes would argue against maybe what I was saying. Just wondering your thoughts on that.
Yeah, I mean, I should say, I mean, I slipped in the poem. There's some old water in the poem for you there, because it is, you know, it is a thing. You know, we need to know what is happening at the beginning in order to work out what's going to happen in the future. And it does depend on the type of flood. So, you know, if you're going to get these terrible flash floods that we saw in Germany, a lot of that, you know, is just because you're dumping a bucket of water in one place and it's turning into a wall of water and rushing down. And that's, you know, topography driven, you know, it's impermeable rock. That is just how that functions. and it's much more important to understand exactly where it's going to rain, which is a really tricky bit at that point. But some of the other floods that we see, and it depends what scale you're at as well, you need to understand the runoff processes because it's really quite complicated, and actually our models don't work very well in certain ways, particularly thinking about groundwater interactions. Where the soil is holding water and where it's releasing water. A lot of that's to do, with complexities of what's under our feet, which most of the time we don't know, we're guessing. So dealing with that uncertainty. So how can you marry getting the runoff processes right in the subsurface and knowing there's huge uncertainty? And I know, I haven't progressed very far on this since my PhD because it's really, really, really tough. You can't say anything definite. So, but I think it's really important, particularly as we start to zoom in. So we're talking about the European program called Destination Earth, which is just about to start. That's a European program which is looking at 1 kilometer grid scale global modeling of the Earth, right? And at 1 kilometer, okay, that's not the centimeter scale where you can start to see kind of preferential flows and things, but we're getting there. And you give it a while and we will be zooming into those areas where those processes are really mattering. Yeah. So yes, for some of the big floods, we're still very coarse, we're making a lot of assumptions, but the future is high resolution. So if we don't keep up with really understanding what those runoff processes are, I think we'll be doing ourselves a disservice in 20 years time.
Good, thanks. I see Martin's hand up. Martin. You're still muted, Martin.
I'm so glad that happened. It's no good. You can't have a talk without somebody not being able to get themselves off mute.
It was your fault actually, Jeff, because the host was not allowing myself to unmute.
Sorry about that.
That's all good. Hannah, that was a great presentation. Thanks. I had a slightly different question. I was interested in your focus on global flood forecasting and then also your focus on developing local capabilities. And I was wondering your thoughts or opinions on how the role of humans in the forecasting process will change over time, and the importance of local knowledge and how that evolution of what humans do in the flood forecast, whether it be building models or operating models during a flood, etc., could be different in developed countries, USA, Germany, etc., versus some of the developing countries that you highlighted in your presentation.
Yeah, I mean, the technological capabilities at the moment are so very imbalanced that I find it very problematic to walk into Mozambique with a global model and say to people, here's our really cool model, go and use that. That's a complete tech drop and it's absolutely appalling. So we tried really hard not to do that and to listen to our partners in the Mozambique Red Cross in particular, and also second people in. So we have a lot of PhD students who will come to Reading and study the techniques, and then we'll go back and teach that technique or work with another system, because that's how you build national capabilities, working really closely with people and just taking a step back. And we should not be in charge of this because they know a lot more about the country as well. I know nothing about Mozambique, but I'm happy to help somebody learn about ensemble forecasting, for example. But it is a very, very tricky kind of a landscape to navigate. It's very difficult to be in Reading as well. It's a very expensive place to live and study. So there's a lot of problems. We've got problems with our government pulling out aid funding at the moment for some bizarre reason. So it is a big mess. I mean, going into the future, I really hope that we have these open platforms. So I refuse to work with closed platforms and pushing for the European system to be open too, because I think this information needs to be open and accessible. There's a lot of talk about joining AI up with physical process models, mapping it all together, and then having humans in the system too. But that again, that only works if we can bring everyone along with us as well. But yeah, I don't have the perfect solution, so it is a massive problem. Did I answer any of your question then?
Yeah, no, it was getting there. I guess another spin on the question is to what extent will the local forecasting centres rely on the Earth system modelling approach? And how does that change the way that humans act in the forecasting process, both in terms of developing their local systems and operating those systems in real time.
I have to say every country in the world is different and in a different place in this with a different way forward, probably. I mean, we have several Earth system models running. So the major weather forecasting centers are all taking this approach already. Okay, so there are like 7 centers issuing these types of at least weather forecast with land surface, so runoff forecasts. So, and they are, that's a global collaboration. Weather forecasting has been doing this for a while. Okay, the World Meteorological Organization has been supporting countries to access those for a long time. So if only hydrology can kind of get together and do the same thing, and perhaps that involves, treating hydrology as a sub-discipline of meteorology, just to be practical, just to make sure people can access it, because it's very, what I've seen is like a load of old computers that have been left. So somebody will come in, help somebody set something up, and then just run away again. It's really important to understand your local river. There is no way that you should be just using the global system. Definitely, definitely. The ideal thing is to use the global system to get that early warning, to get that overview, and then perhaps feed that into a more local model, or run a separate local model that's got all that local knowledge in it, and the nuance of who's going to release the reservoir, or things that you just can't capture at the global scale yet. So that, a seamless system that uses the global techniques what they're good at, but also has the local knowledge and the local systems is the ideal setup. And that should have happened in Germany. Right. So
Well,
this is what
yeah. And maybe
frustrated
one last question on that point. This is from Wouter Nobin, who's typed into the chat. Thank you, Wouter. And we'll end with this after your answer and transition to the early career discussion, Hannah. Hannah, thanks very much for the talk regarding the European flood warning forecast system and the recent floods. Can you share some thoughts on the political constraints of making the EFAS forecasts publicly available? What is the current status, and will this change after the recent events? Personal anecdote, Wouter's brother lives near the Meuse and was asking what was going to happen there, and I couldn't figure out how to access the forecasts.
Right, because they're not open yet. They are not, and it's absolutely appalling. I hate it, having worked on a system for so long. I mean, the global system is open, thank goodness, but there is a lot of political constraint. There's a lot of defensiveness from member state countries, I suppose, because they are not, they are responsible for issuing the warnings. They don't want additional information out there because then their trusted voice is interrupted.
Right.
So that notion of having a trusted voice from the national capability who are responsible for issuing warnings is very important too. So you have to take that into account.
Yeah.
But we're moving into the area where Google is issuing a flood forecast as well. So it's going to become reasonably irrelevant quite soon. So I would hope that there is some backlash against this closed system, but it is very political. Sadly.
Yeah. Okay, well, Hannah, on behalf of the whole group, thank you so much for a really exceptional talk. I'm hearing clapping all through the ether.